Hey class, let's take a look at electrochemistry part 2, voltaic cells, batteries. How do they work, what goes into them, and then of course the math behind them. We will do several Pogles, a lab, and a few other things that will help you understand this material. A voltaic cell, or a battery, transfers electrons through an external pathway, not directly between reactants. And if you take a look at this picture on this slide, this is an example of what we're going to do in class. You have one metal in its solution, a different metal in its solution. The two metals are connected by wires, usually to a voltmeter so you can measure voltage. And then typically what is in between the two beakers is a salt bridge. So how does this work? The zinc is in zinc solution, the copper is in copper solutions, and the electrons are going to leave one of those metals and flow toward another metal. And then of course, once electrons are flowing, you have electricity. We'll go ahead and take a look at how do you know which way the electrons are going to flow. Before we jump in too far, let's just take a moment and understand some vocabulary. I find that this unit isn't really difficult for students if they understand the vocabulary. An electrode is just the metal that's connected by an external circuit. So in the previous picture, the pieces of metal sticking up out of the beakers. The anode is where oxidation occurs. And the anode is negative because the electrons are leaving. Think about anode and oxidation. Oxidation, oil rig. Oxidation is the loss of electrons. So the anode is losing electrons. That's where they're gathering, and that's why it's negative. Well, the cathode is where reduction occurs, and the cathode is positive. And that's why the electrons want to flow from the anode to the cathode, because they want to go from negative to positive. A half cell is just half of a voltaic cell. It's one metal in its solution, and one side is oxidation and the other side is reduction. So where exactly do the electrons come from? And what exactly is happening? Believe it or not, there's a lot happening in this picture. Zinc is oxidized at the anode. And if you recall from the first part of the lesson, if you were to look up zinc and copper, their reduction potentials, you would find that copper is more positive, and the more positive value is reduced. So we know zinc is oxide, so that's going to be the anode. The electrons gather there and they flow through those wires over to the copper. Well, then they go down the copper and into the solution. Now, what's the solution? It's probably copper nitrate. So there's copper ions and nitrate ions in there. Well, those electrons are negative. They go down the piece of metal to the solution and they connect with the positive ion, the copper ion. And this removes the ions out of solution and actually creates copper on the copper plate. So if you were to let this sit for a while and come back and look, the zinc is going to look like it's been eaten away, and the copper is going to look like it's grown, and the copper is being reduced. So what's happening? In the blue solution, the copper ion concentration is decreasing, and so that solution is becoming negative. Same thing backwards is happening over at the other cell. If the electrons are leaving, that solution is becoming positive. Well, if that solution becomes positive in the zinc, so the zinc is sitting in something positive, are the electrons going to want to go away? No, the electrons are going to want to go straight down. So we need a way to keep both solutions neutral. We don't want the anion solution to become negative or positive, and we don't want the copper solution to become negative. So the salt bridge is usually, in our case in the lab, is just a piece of filter paper soaked in usually potassium nitrate, but it provides ions to the solutions. So in the copper solution, the positive ion is leaving and it's going onto the metal and being reduced. So the positive ions, the potassiums, are coming off the salt bridge and going into the ion. On the other side, the anions, the negatives, whatever is on the salt bridge, could be potassium chloride, could be potassium nitrate. Let's go with nitrate. Those nitrate ions are going to go into the anode solution and keep it neutral. So there's a lot going on, and if you don't have a salt bridge, it's just not going to work. But just remember that the anions go toward the anode, and the cations go toward the cathode. And that helps out a lot. And again, don't panic. We're going to spend quite a bit of time with some problem sets and some Pogles and some other things that will really help you solidify what's happening, where everything is going, which way the electrons are flowing, which way the positives and negatives are flowing, and it'll make a lot more sense, I promise you. There's a lot to unpack on this slide, so let's dive in. We can calculate the cell potential under standard conditions. And it's really, I promise you, not that difficult. Basically, if you hooked up that zinc to that copper, what would the voltmeter read? That's what we're talking about when we say cell potential. Well, the electrons flow because there's a difference in potential energy. There's a higher potential energy in the anode than the cathode, and so the electrons flow spontaneously toward the cathode. A cell potential is a difference between the two electrodes. So if you had zinc in zinc solution and zinc in zinc solution, there's no difference, so electrons aren't going to flow. Another term you hear quite often besides voltage or cell potential is EMF, electromotive force. In fact, my dad, who was born in I think 1943, he went to DeVry Institute of Technology when he was younger. And every time I talk to him about voltage and whatnot, he's like, it's electromotive force. So the old timers are going to tell you it's not voltage, it's not potential difference, it's EMF. But it's basically just the potential difference that pushes electrons through the external circuit. See, in electricity, you should take physics. In electricity, voltage is what's pushing the electrons. Current is how many electrons are flowing. So you can have a big push, but if there aren't that many electrons to flow, then the current is really, really low. We're just focusing on voltage. And voltage, of course, is measured in volts. You can label that a V or volts. Cell potential is always positive. Otherwise, the battery doesn't work. If you get a negative, you've got your wires flipped backwards because it's not going to go in a negative direction. It's just not spontaneous. The magnitude of the voltage depends upon three things: the reaction that's occurring, the concentration of the reactants and products, and we'll take a look at that in this unit, and temperature. Reactions occur at standard conditions. You're going to hear those terms a lot in the book, and that's just so that you know what you're dealing with. Standard conditions is room temperature, 25 degrees Celsius or 298 K. All of the solutions are 1 molar. So when we do our lab, all of our solutions are 1 molar and at 1 atmosphere of pressure. The standard conditions, when you have a cell potential at standard conditions, we label it capital E with a little o up here. Remember that O means standard. You've seen it before with enthalpy and entropy. And then we just write cell down below to talk about the entire equation. So how do we calculate E? It's actually pretty easy. It's found by examining the standard potential for each half cell. And we use an appendix in the back of our book, or online resources are also available. To calculate the standard cell potential, you literally are just subtracting. You take the number that goes with the element that's reduced, and you subtract the element that's being oxidized. Always write the reactions as reductions, even if the reaction is an oxidation. Changing the stoichiometric coefficients doesn't affect the value of the EMF at all. So if you notice in the appendix, they're all listed as reductions. We want to leave them as reductions. All you have to do is figure out, either based on looking at the equation, who's gaining electrons, who's losing electrons, or by looking at the values. Remember, the one that has the more positive E value is reduced. Pick the one that's reduced, subtract the one that's not reduced. Well, what do the positive and negative values mean? Again, the more positive the value of E, the greater the tendency for reduction. The value for the reaction at the cathode is always more positive than the anode, and this is what allows the electrons to flow spontaneously. If you think about why we have batteries, it's to do work, right? To play your, okay, I'm going to date myself, to play your boombox or to play your little Walkman so you can put your cassette tape in there and put your headphones on as you walk to class getting ready to take a test. So believe it or not, we can relate all of these things to delta G, free energy. When E is positive, it's a spontaneous process. It happens. If you calculate E and it's negative, it's not spontaneous. This is not going to result in a battery. And you want to apply the activity series to figure this out. And again, you can also look at the reduction potentials I explained on the side before. But what if you just have the activity series? You need to look at the equation you're given. And in the reactant side, look at which one is the solid and which one is the ion. Then look at the activity series. The solid must be above the ion. Because what do we want to happen? We want the solid to give its electrons to the ion. So then the solid becomes an ion, the ion becomes a solid. So the only way that's going to happen is if the solid is above the ion on the activity series. For example, nickel is above silver. So nickel will give its electrons to silver. Nickel's oxidized, silver's reduced. If you flip it around, it won't work. To calculate E for this particular reaction, go ahead and look up the values, see if I'm correct. Because silver is reduced, it has a value of 0.80. It goes first. And then you subtract nickel's charge. Well, notice nickel's a negative. So the only thing tricky about this math is you're subtracting a negative number, which becomes positive. So you just add the two and you get plus 1.08 volts. Because this is a positive value, this is spontaneous, this reaction will go. I think one of the reasons I really like teaching this unit and the fact that it's at the end of the year is because it ties so many things together that we've learned throughout the year. You can relate the electromotive force to free energy and K, the equilibrium constant. How cool is that? So here's the first equation. You can link Gibbs free energy and electromotive force by using this equation. Delta G equals negative NFE. N is the number of moles of electrons transferred in the balance equation. So if you look at the half reactions, remember you can't add half reactions unless the electrons cancel out, and that's how you'll figure out your number of electrons. F is Faraday's constant, 96,485 coulombs per mole or joules per volt mole, different labels. Remember that the units on delta G are joules per mole. Normally delta G is calculated in kilojoules per mole. But when you do this equation, you do get joules. So pay attention. The book might ask you to convert to kilojoules. Well, when E is positive, we know that's a spontaneous reaction. So G is negative, because remember, G negative is spontaneous. So when both E is positive and G is negative, spontaneous. And we can also relate this to K. And there's several equations listed below. E is equal to the delta G divided by negative NF. And you could do some substitution and just go ahead and take a look at those. We will play with some of these equations. We'll actually use them in the lab. And this is going to get us into the next equation called the Nernst equation. What if you don't have standard conditions? Can you still calculate all these things? You bet. You guys know that eventually all batteries die. Why? Well, as a voltaic cell is discharged, the reactants are used up, products are created, and the concentrations change. That's hard to say. And so when your electromotive force decreases and E equals 0, the battery is now dead. It's not going to have any more juice to keep going. So how can we calculate EMF under non-standard conditions? What if we don't have 1 molar solution? What if the temperature is different? Usually we're talking about concentrations. And in our lab, we're going to use the Nernst equation several times. And usually it's because we don't have standard concentrations. So take a look at the Nernst equation. There's a couple of different versions of it, and it really just depends on what you have. But what I want you to focus on right now is the Q. You have to calculate Q. So you have to have the balanced equation. And remember, when you write K or Q, we do not include solids and liquids. Usually all Q is composed of are ions, whatever ions are in the solution. So like I said, we'll practice this quite a bit. The log looks scary. It's really not, I promise you. And you'll get quite a bit of practice with Nernst. I was actually going to end there, but I think I want to talk a little bit more about the Nernst equation and Q. Remember that Q is products divided by reactants. And as those reactants get used up and the products are made, Q gets bigger. Remember, products over reactants. This is getting bigger, this is getting smaller. Your whole answer is bigger. This is really important. I know this is on the test. As Q increases, E decreases. When you play with the Nernst equation, you will actually see this. And it's just the nature of the fact that as Q gets bigger, that part of the equation becomes bigger, and so you're subtracting a bigger number and reducing E. Delta G equals negative NFE. Well, when E is 0, dead battery, G is also 0, equilibrium. When E is 0, the cell has reached equilibrium, no net reaction is going to occur. But how do you create more voltage? There's two ways you can create more voltage. And if you think about the equation and you think about Q, this makes sense. If you increase the concentration of the reactants, you're making your denominator bigger. That's going to make that value smaller. And when you put in smaller numbers into the log, it's going to make your overall value actually go up. If you decrease the products, again, now your top number is smaller. It's also going to result in the same thing. Believe it or not, this is an application of Le Chatelier's principle, and we'll see this in our lab. So go tackle all of your problems. Let me know what questions you still have, and I think you're going to be surprised how much sense this makes.